Hey guys, welcome back. So this is going to be our second video on our geosphere, which is the Earth, the rocks, the center and core of our planet. And so what we're going to look at today is some of the processes that occur inside the planet that both keep the geosphere active and functioning, but also are involved in the formation of geological features such as volcanoes, mountain ranges, earthquakes, and we're also going to talk about the plate tectonics and how that shapes the crust of the Earth where we live. All right, so let's go ahead and get started. So just a quick review. We want to remember that we have different layers to our planet. So starting off, we have the inner core, which is solid, the outer core, which is fairly liquid, followed by the mantle, which extends from the outer liquid core up to the top, and that top layer where we live is the crust. All right, but there's this boundary layer of the mantle that consists of hot rock that's moving very, very, very slowly. Think about like maybe silly putty almost. And that's the asthenosphere. It is a layer of upper mantle that's moving kind of slow. And then the topmost layer of the mantle and the crust, that's this thing called the lithosphere. And the lithosphere is part of what you live on, all right? That uppermost layer of the mantle where it's hot, it's heated, it's somewhat malleable, but it doesn't really move. It doesn't flow the same way. That's what's getting pushed around by the motion inside the mantle, all right? So let's break this down a little bit, okay? So let's zoom in a little here. So you have the lithosphere, and that includes the solid rock of the crust and then this hot rock that's underneath that. But then you have this stuff called the asthenosphere, and it's a soft layer of mantle on which pieces of the lithosphere move. It is made of solid rock, but it's like putty. Again, like imagine silly putty, all right? You can push it, you can move it around, and motions of convection currents inside the mantle will move that, all right? It does move, and it's moving continuously. The continents are shifting, the plate tectonics are moving, and they move about the same rate that your fingernails grow, which is about 1 centimeter per year, or a little under half an inch a year. All right, so let's take a look. So first off, we need to go ahead and make sure we define convection. So convection is the circulation of heat in a fluid. All right. Now, there are other ways that heat is transferred, and I want to clear those up here really quickly. So conduction is the transfer of heat through direct contact. So convection would be the water inside a pot of boiling water. If you ever look at a pot of water as it boils, you'll see that you've got water rising to the surface, and it's that bubbling, rolling action that you have in a boiling pot of water. But conduction is what you would find if you were to grab the handle of that pot directly. So that is transfer of energy through the direct contact of two materials. And then lastly, you have something that is radiation. Radiation's a little different. That is the transfer of energy through space as a wave. So the best example of this is infrared radiation, which is just hot light, basically. Okay? So different wavelengths of light. And you can experience all of these things right here in Arizona. Just step outside when it's 110 degrees outside, and you'll experience them really quickly. So conduction would be how you burn your feet if you walk outside in socks or without shoes or something like that to go to the pool. Radiation is how you can notice that it is much hotter when you're out in the sunlight versus in the shade. And then convection, well, that would be, say you hop into the pool and you notice that it's kind of warm on the surface, but the bottom of the pool is nice and cool away from that. But as things happen, it starts to circulate, okay? So that is convection, conduction, radiation, all right? Today, though, what I'm going to do, and in the next couple of slides, is I'm going to focus very heavily on convection. So convection currents are usually going to move in a circle, and I'm going to show you how they flow. All right, so what I want to do here is I want to take a look at how we can see that convection plays a part in the geologic processes that we see. So we have the lithosphere, that is the crust and upper mantle, all right? It's divided into separate plates, and those are the tectonic plates that we talked about during our last class, and they move very slowly in response to those convecting currents. So I know that was a lot on the last slide, but the part that you need to be aware of and you really need to think about is the convecting currents. And that's that circular motion of heat rising and falling and rising and falling, and it creates this circulating cycle. Well, as that hot magma rises up, reaches the upper layer of the mantle, reaches the lithosphere and asthenosphere, it pushes against that. Just like how a water current can push a leaf down a river, it's the same idea. So if you have two currents that are pushing towards each other, you can get continents moving together. If you have two currents that are spreading apart from each other, you can get continents moving apart from one another. So this is how you see this difference of the shape of the Earth over time. And over time, our continents have drifted and moved apart as a result of this kind of convection motion. All right, so let's take a look then at some of the things that this does. All right, so now what I need to look at here is how that convection current and movement of the plates shapes what we're able to see on the surface. All right, so first off, convection currents can move plates towards each other, which is going to cause something called subduction. And this right here is a subduction zone. So this is caused when you have a convecting current that is pushing the plate this direction. So it's pushing one plate towards another one. And generally what you'll have is you'll have a oceanic plate, or the oceanic crust, so that's the crust of the Earth under the ocean, being pushed under the crust of the Earth for a continent or continental crust. You get this oceanic trench forming there, and that's where you can find some of the deepest parts of the ocean, and you end up with one plate diving under the other. Now, here's the thing. As that plate gets pushed under, it's not just rock that's on that plate, because you have to consider this is all the sediments of the ocean here. It's got compressed stuff that's washed off of land. It's got compressed matter of water getting trapped in there. It's got hydrocarbons and oil and stuff like that. That's things that we would normally drill for. And it's all squished down in here. And some of that is actually going to melt at a lower temperature than a lot of the mantle around it. So you get this melting effect here. And you suddenly have this liquid that is much less dense, melts at a lower temperature, but is still very, very, very hot as it's being pushed into this hot mantle. And that magma will now rise up, and you'll get a subduction volcano, or a volcanic arch. This is incredibly important for the Earth because, remember I said, this is all that stuff that was washed down in here. And that can contain carbon and phosphorus and sulfur and nitrogen and all kinds of other useful materials. Well, guess what? That recycles it back up to Earth. This material that was lost in rock and was trapped on the bottom of the ocean, it's now being recycled up onto our continents. And this is why volcanic soil sometimes is very, very, very useful for growing food in, because it has all those trapped minerals in it that are being recycled back up to the surface. And this is one way that the Earth renews itself. So that's a really cool thing. And that's how we can get these volcanic arches that go like all the way around the Pacific, where you find volcanoes literally all around the Pacific. That's because that Pacific plate's being squished under all of the continental crust around it. All right. But the next kind that you need to look at is where the ocean plates are moving apart. And you do get that as well. In fact, in the middle of the Atlantic, you've got something called the Mid-Atlantic Ridge. You get an ocean ridge, and that's where you get this dividing area, all right? You get a spreading ridge, which pushes them apart, all right? That's a divergent plate boundary. That's where you have two plates separating from one another. And that separation of the plates causes a ridge or a line of volcanoes to form all along it. And again, that's because you've got a rising magma plume, you've got them separating and swirling there, and you get a pushing of the plate in two different directions. All right? So it's literally pushing it apart. Like if you can imagine, like if you were working dough or something like that, and you push down on it and you push it apart, well, it's like that. It's just in reverse is all. Okay? And then lastly, you can also get convecting currents that will bring magma to the surface and form a hot spot. So you have a volcanic arch that can form there as this plume of magma will rise up from deep in the mantle, close to the mantle's core, or even right off of the inner or the outer core of the Earth. And that rises up and creates this hot spot that moves there. And that's how you get volcanoes like you have at Hawaii. Hawaii is a hotspot volcano, all right? It is caused by a place where you have a rising plume of magma. Now, you're probably thinking, Mr. Davis, what causes the hotspots to form in these specific points? And I'm very happy to tell you, I have no idea. In fact, we're not really totally sure why hotspots form where they do, but we can definitely see their effects, all right? It might be just this is one way that the Earth releases heat regularly, but this is a way that another type of volcano is formed, and it is, again, how you can have that rising magma coming to the surface, creating another volcano there. All right, so let's take a look at these two images of the Earth and look at the layers here. And you should start to notice something very quickly, all right? You have a rating on one side of this image here that shows you where you are, and it gives you the name, the crust, upper mantle, mantle, outer core, inner core. And you'll see that you have these depths on them in kilometers. All right, great. So that tells us how deep you have to go to get to each of those layers. But there's something else that this tells us. What do you see on the other side of this image? And there you can see a temperature. Okay, all right. So 600 degrees Celsius, that is incredibly hot, all right? That is, to put things in perspective, going to get your temperature hotter than pretty much any oven you'll ever encounter can do. This is hot enough here to melt glass very easily. And then as you go up into these upper and upper temperatures, it gets hotter and hotter and hotter. And at these deeper depths, you'll notice that it increases in heat. So that's what we need to look at with the Earth. As depth increases, temperature increases as well. And we can see that in the physical properties also, because if you remember, when I said that the upper part of the mantle is like taffy or putty, it's softer, it's squishy, it is able to move like that, but it's not a liquid, all right? It's still semi-solid. But as you get closer and closer to the outer core, it becomes fluid. And the outer core is actually a liquid. It flows pretty much with about the same consistency as pancake syrup. And we know this because by listening to the seismic vibrations from earthquakes around the world, we can see how those vibrations change when they pass through different parts of the Earth. And by measuring that, we're actually able to get a rough idea of the density and viscosity of that by how sound moves through it. Okay, great. But what else is going to happen here? And it has to do with how the inner core is. So if you guys remember, the inner core is completely solid. Even though it's the highest temperature, it's solid. Why? Well, let's take a look at this graph. All right, so we have depth, we have pressure in gigapascals. Let's take a look at the relationship between depth and density and pressure. Okay, so here's your depth, here's the crust, the mantle, the core, and we want to look at density. All right, so density is grams per cubic centimeter. So if you have, 1 centimeter cube on each side, all right, you can see that this has a density of about 2.7 grams. But when you get to the mantle, that goes up anywhere from 3.5 to 5.5. So that can more than double. Now, keep in mind, the mantle is a big area, so there's a lot of variation in there, all right? And then when you start getting into the core, you have anywhere from 10 to 12 grams per cubic centimeter. So that density is going up and up and up. And the reason why is, well, we got to look at the pressure. How much pressure in atmospheres? So at the very, very top of the crust, where you're sitting right at sea level, 1 atmosphere. But going down through the earth, when you have more and more and more rock pressing on you, you have a higher and higher level of pressure. And that can get up to about 1,000 atmospheres. Then you start getting into these numbers here. And this is anywhere from 1,000 to 1,000,000 times the pressure that you feel on you right now. And that's the other thing to keep in mind. This is 1,000 times as much pressure that you have on you at the moment. This is 1,000,000 times as much pressure as what you have on you. And this may not seem like much, but this difference here is just as great. All right, I mean, it's a massive amount of pressure that you get up to there at that very end. All right, so as you can see here in the pressure in gigapascals, it's another 10 times as much there. And once you're under that much pressure, when you get down to the center of the core, you are just squished down till you are as small as can be. All right, it is under so much pressure that it forces it back into being solid. So what's the overall relationship that you find as you go from here, from the crust all the way down to the core? So what is the overall relationship we have here? Well, you should be able to say that density and pressure both increase as depth increases. And this is the same picture that we had from the very beginning of the first presentation on the inside of the Earth. You have your crust on the outside, your mantle, your outer core, your inner core. And as you get down to that inner core, that pressure has increased so much that this becomes solid. Okay, just again, remember, temperature and density and pressure increase as depth increases. So all of these things, all 3 of those factors, go up as you go farther underground. All right, and that's the critical thing that you need to take away from this, that the deeper underground you go, the higher all of those values will be. All right, so real quick, let's see if we know this one. Pause your video right now. Tell me, which layer of the Earth has the greatest, the largest temperature, pressure, and density? Pause your video if you're not sure. Think about it. And what you should say is the core. Yeah, the core has the greatest pressure and density and temperature in the Earth. All right? And you got to know that that's all going to be the highest once you get to the center of the Earth. Alrighty, so let's go ahead and get to our summary. All right, this is the last part, guys, I promise, for talking about, what's inside the Earth. All right, so this is going to kind of finish up our geosphere kind of stuff. Next, we'll be talking about some other parts of the Earth, but let's finish up here and see what we got. The Earth is layered with a lithosphere, or crust, and uppermost mantle. A convecting mantle, that means it's got a circulating current. And then finally, you have a dense and solid metallic core. Remember, that's made of nickel and iron primarily. Those 2 elements are the most abundant in the core. All right? The pressure and density is going to increase as you get towards the center. and that's going to end up increasing all of those factors. So that's where you're going to have the hottest temperatures, the highest pressure, highest density. So your core is solid, but it's also the hottest. All right, guys, that's going to finish up this video and this lecture. I'm going to go ahead and end there for today. Coming up next, we're going to start looking at the atmosphere, and we're going to look at how the atmosphere will then interact with the lithosphere. So that's the next part of this. All right, take care, and I hope you have a great day. Later.